I
just realized I have an extra pen.
I'm picky about my pens too, though.
So question number three, that is how you are actually supposed to write. Like the basis for the column are the ones which have, it is so easy to get a basis for the column space. So you just pick the ones which have the pivot position. So in this case, it is the first one, the second one, and the third one. So this is the first, the second. And then you put it like this. So you put this one. That's how you write it. And then for the basis for the null space, so you need, so it is already reduced. So back you need to add what? This zeros here. So it is already reduced. If you can see the pivot positions are here and here. So above it there are zeros. What you need to do is you need to check the basic variables and the free variables. And then you write it like this, and then now you come and put it in form. So, and then finally you write it like this. So this is a basis for the analysis. Then also dimension must include dimension for the column space of A and the number of vectors. So 1, 2, 3. So there are 3. The dimension for the column space are the number of vectors. The null space are the number of vectors here. So dimension of null space. Then the round is equals to the dimension of the column space, which is equals to E. Any question there? Okay, the next one is here, and the standard basis is the standard matrix is just written like this. So you write it like that. So you just bring this as a column and then you put it back. Find T of u when u is equals to that. So T of u is basically equals to A what? AU. So T of u is just the same as AU. And this is what? This is A. So that is A. So then you now come and do what? You multiply. So you multiply A and what? And U. And that is what you get. So this is basically for this section. And then determine whether the transformation T is 1-to-1 or not. Justify your answer. So you need to reduce this one. So I said if it has the pivot positions in each of the column. In each of the column. So if it has pivot position in each of the column, then it is what? It's 1-to-1. If it has a pivot position in each of the row, then it is what? It is 1-to. So in this case, this matrix here is neither 1-to-1 nor what? 1-to. So since we don't have pivot position in each of the rows and also in each of the columns. So make sure you remember that. Okay. Number 5. In fact, that one is so easy. I think one of you was making a mistake on the getting the determinant of C, which is -3, and then plus what? +2, which is equals to -1. And then number 7 there, it is also the same thing. So number 7 is actually the application of what? Linear independence and linear dependence. So if you have a pivot position in each of the columns, then it means that when we have trivial solutions only. So if you have the trivial solutions only, then it means it is what? It is invertible. It is invertible. So if you find a column which has 0, 0, so it's application of linear independence and linear independence. Like for instance, this one has 0, 0. So if it is linearly dependent, then it is if it is linearly dependent, then it is singular. Okay, so that was it. I think the third exam will be harder than this.
I would expect it to be harder. Hopefully not too hard.
Yeah.
I like that test.
So it was so the final part, the third exam will be chapter 3 and 4. 3 and 4. So it might be longer than this one. So this one I was solving here and I took only 20 minutes. So I was like, wow. I made a very simple exam. Anyway.
I was here forever though.
Yeah.
I was here for a long time. I was here like 55 minutes.
So the third exam.
Well, I double checked everything. I went through them all, then I went through 2 of them.
So the third exam might be longer than.
Because I did make some mistakes, but
this
then I
one.
fixed them.
So make sure you read well on chapter 3 and 4. And then for the final exam, it is the cumulative. So I hope we'll reach section chapter 5.3. That is my target. So I want us to make sure we reach the diagonalization of the matrices. That is actually so important, the eigenvalues and eigenvectors. So I'll make sure we go a little bit faster. Since I've noticed we have a lot of holidays. Okay, so let's continue from where we left. And I hope we will try finish section 4.2 and maybe we do something on 4.3. So we were on polynomial. We were on the polynomial. So we say that polynomial is of that form where the A is the A naught, A1, An are the coefficients. The coefficients. And X is basically the indeterminate. And then we say the degree of P is n if An, this An actually is the highest power of X, the highest power of X there in the polynomial. So it is n if An is not equals to 0, and it is minus infinity if this P here is 0. So if this polynomial here is equals to 0, then the degree of that polynomial is negative infinity. Okay, another thing to note is, so two polynomials are equal if they have the same degree and same coefficient for each, let's say AK, for each AK. So two polynomials are the same if they have the same. Another thing to note is so you can also add the polynomial. So you can also add the polynomial, and then you can also multiply the polynomial by the constant coefficient, constant term, or the constant term. So you can add the polynomial. So if you have the polynomial, let's say P and Q. If we have that polynomial P and Q, then where P of X is equals to, let's say, AN XN plus all the way to plus A1X plus A naught. And Q of X, let's say to be equals to BM XM plus all the way to B1 X1 plus B naught there, right? You have those polynomials there. Then for this one for you to add this one, then P plus Q of X, P plus Q of X is equals to, so this one is equals to A naught or AN, let's start from AN XN plus AM plus 1 XM plus 1 plus AM plus BM XM plus A1 plus B1 X plus A naught plus B naught plus A naught plus B naught if M is less or equals to N. M is less or equals to N. In this case, N is greater than M or they are equal. So AN, XN, so if you're adding the two polynomials there. Also, BM XM plus BN plus 1 XN plus 1 plus AN plus BN XN plus A1 plus B1 X plus A naught plus B naught if M is greater than N. If M is greater. N is greater than N. 4. Also, we can multiply this polynomial by the constant term. If we can multiply C, if we have, let's say, and the multiplication of a polynomial by a real scalar is, let's say, C multiplied by P of X. This is basically the same as CAN of XN plus, we continue like that, plus CA1 of X plus CA naught. So multiply, you can also multiply by the constant, real constant. So real constant and 1, 2, 3, up to infinity. Okay, so that is the polynomial. So in this case, this polynomial is also a vector space. So it satisfies the 8 axioms that we already stated. So they satisfy the 8 axioms. So let's look at an example. Example number 3. Let's look at example number 3. The sets of all polynomials with real coefficients. The set of polynomials with real coefficients is written in this form. It is actually the capital P. And this is the same as an xn plus an minus 1 xn minus 1 plus an plus a1 x plus a naughts, such that a naughts all the way to an are elements of real number, and n is greater or equals to 0 is an integer. So the set of all polynomials with real coefficients is all that. So it is basically the polynomial. If they have the real coefficient, we write it as P capital. So this P capital is a vector space under addition of polynomial and the multiplication of a polynomial by a real scale. So it satisfies the 8 axioms that we had. Like, for example, if for the 0 polynomial, so number 1, for the 0, like what we had for the 0 vector, let's say the 0 vector in P, which is in this, is the 0 polynomial. This 0 polynomial. So that 0 polynomial has the coefficients of 0. So the coefficients are 0. Number 2, the negative. The negative vector of P, let's say P of x, equals to an xn plus a1x plus a naught in P is basically negative P of x, which is the same as negative an xn plus negative a1 x plus negative a naught, and it's basically the negative vector. So, like we have said, it follows the 8 axioms. Those are basically 2 examples that you can get from axioms of vector space. Okay, now let's come to the next section here. And this section we have already done, but we can still see how we can review it. So number 2, the subspace. Subspaces of a vector space. Subspaces of a vector space. So we already defined this, and let's just review it. So we said a subspace of a vector space, let's say V, is a subset which we named as W of V, which is a vector space under the addition and scalar multiplication. So W is a small a subset of the whole vector space. So it's actually this W here. satisfies the 8th axiom that we had. So it basically satisfies the 8th axiom because you are just picking a small section of the whole vector space. The whole vector space. Okay, now let's look at a theorem here, which is so important. And I think it is important we look at it. And this is basically 2.2, and this is a theorem. And this is what we call the subspace test. A subspace test. So it tests subspace. So subspace test. Now we let V be a vector space, a subset W is a subspace if and only if a 0 vector is an element of W and Cu plus dV is also an element of W for any C and D, which are real numbers, and U and V are elements of the subspace. So we also say this one is a what? We also say this one is a vector space. So basically, this satisfies the whole vector space. It satisfies the 8 axioms. It satisfies the 8 axioms. So let us prove this. So let's prove this, but it is not so important, but let's prove it. You need to have it in your notes at least. So let's prove this. So in mathematics, if you are told if and only if, then you prove the forward and the backward direction. So there is a forward and a backward direction. So start by starting from the forward direction. So in this case, it says, let V be that a subset W is a subspace if and only if 0 vector is an element of W and CUDV is an element of W for any of these. So you need to prove that direction, and then you need to prove coming back. Okay. So if it is if and only if, then you need to prove both directions. Okay, let's prove the forward direction. So in this case, we can let 0W, okay? 0W is a vector in W, denotes the vector of W, the vector of W. Then 0W is actually equals to 0W plus what? 0W. Just a second. And 0W is also equals to 0W plus what? Plus 0 vector. Plus 0 vector. Now, since 0W plus 0W is equals to 0W plus 0, then 0W is equals to 0. And hence 0 is an element of W. 0 is an element of W. The other one, if C and D is an element of real number, and U and V are elements of W, then CU and CD and CV, sorry, and DV are elements of what? W, are elements of W. And if you add the two of them plus DV, both of them are in what? They are in W. So that is the forward direction. That is the forward. And we come back, backward direction. So we write it like that. Backward direction. Now, if we so you're actually starting from this. You're starting from here and then you go back, okay? So you're starting from this. So if you let U and V to be elements of W, if you let U and V be the elements of W, and C is an element of real number. If C is an element of real number, then U plus V. U plus V is basically the same as 1U plus 1V. And these are what? These are in W. Basically, those are in W. So 1 is basically constant, an element of real number. And CU is the same as CU plus 0, 0 vector. And CU plus 0, 0 vector is basically this in 1. It is in W. And that is the proof. That is the proof. Now, the conditions 1 all the way to 3 in your axioms that we wrote. These axioms here, 1 to 3. 1 up to 3, and also 5. And 5 to 8, and 5 to 8 in definition 1.1 are true for W. So those definitions are also true. So they satisfy those. Now for number 4, for this number 4 here, if we let U to be that, the elements of V to be negative like that, then in this case, for the number 4, if U is an element of W, if U is an element of W, then negative U is the same as negative 1U. And this is also in what? This is also in W. That is in W. And U plus minus U is equals to what? 0 vector. And this is in what? In W. So that is in W. And that is the what? The negative vector. It's the negative vector of U. So negative U is the negative vector of U. The negative vector of U. Okay. So this proves that W is a vector space under addition and scalar multiplication on V. Scalar multiplication. All right, now let's go to the next example. Example 4. Show that W1 and W2 are subspaces of a vector space V. Then W equals to W1 plus W2, whereby W1, which is that, plus W2 is that, such that W1 is an element of W1 and W2 is an element of W2. Is a subspace. So you can also show that this is a subspace. So you need to check whether it satisfies for this one to be a vector space. Then you need to check whether it satisfies the axioms of the vector space. So it should satisfy the axioms. So basically, you use the subspace test. In this case, you just use the subspace test. So what you need to do is, for the subspace test, then it is just the zero vector and also the CU plus DV are elements of that. So for this, so you use the subspace test. So let me give you a sketch. So the proof is just a sketch. So what you need to do is you can let zero. So you start by getting the zero to be the element, zero vector to be an element of W1, and also zero vector is also an element of W2. Okay. Then W0 vector plus zero vector is the same as what? Zero vector. And this is in what? In this W. So it is basically in this. It is in that. So that is the first. So you need to check whether this actually satisfies the first subspace test, and it is satisfied. Because if this is in W1 and also this is in W2. So when you add the two of them, then you still get zero. And this zero is in W, and this W is what? This, and this is the addition. Okay. Also, if we let U and V to be elements of W, the elements of W, and C and D to be elements of real number, just the way we did in the subspace test. Then find U1 and V1, which are elements of W1, and U2 and V2, which are in W2, such that U is equals to U1 plus U2, and V is equals to V1 plus V2. V1 plus V2 is U and V. So therefore, then Since CU1 plus DV1 is in W1 and CU2 and plus DV2 is in W2, then CU plus DV is equals to CU plus U1 plus U2 plus D V1 plus V2. V1 plus V2. And basically, this is in what? This is in W. So therefore, shows that my subspace F, then this is a what? This is a vector. So this is a vector space. So by subspace test, then W is a subspace of W is subspace of another example on the polynomial. So example number 5. Example number 5. Show that W is equals to P, which is an element of the polynomial with real coefficients. And this is a small p, such that P of 0 is equals to 0 is a subspace of P. Show that this W is in P. Show that it is in. So using the same subspace test, so you can prove using the subspace test, you start by the 0 polynomial. So we know that since the 0 polynomial, which you can write as the capital 0, satisfies 0 and 0, 0 of 0, which is equals to 0. Then the 0 is an element of what? W. 0 is an element. The second one, the subspace test, if we let P and Q to be the elements of the, in this case, of W. If we take this P and Q to be the elements of W. And C and D to be elements of real number. To be the elements of real number. Then CP plus DQ of 0. CP plus DQ of 0. You can now distribute 0 inside. Is the same as CP of 0 plus DQ of what? 0. And these are basically the same as C0 plus D0, and this is equals to what? 0. And so CP plus DQ is an element of what? It's an element of W. So then, so by subspace test, W is a subspace of the polynomial with real coefficients. So it satisfies the two Okay, now let's look at definition 2.3. And this one we already have this. And it said we let V be a vector space. Then V1, V2, all the way to Vn or Vp is a linear combination of V1, V2, all the way to Vp, where we let V be the vector space of V1, V2. And, sorry, let's remove this. Let's start it again. 2.3 definition. If we let V be a vector space, V1, V2, all the way to Vp, and these are vectors, and these are in the bigger V, and C1 all the way to Cp is an element of real number, then number one, the expression C1 V1 plus all the way to Cp Vp is called a linear combination of V1 all the way to Vp, where the scalars C1 all the way to Cp are called what? Weights. Number two, the sets of all linear combinations of V1 all the way to Vp is called a span of V1 all the way to Vp, which is written as the span of V1 all the way to Vp. These are commas, whereby this is basically the same as C1 V1 plus Cp Vp, such that C1 all the way to Cp are elements of real number. So that is what we already defined last time. Now, then this definition will now lead us to how can we write the polynomial? So how can we write the polynomial like this? So and this will lead us to example number 6. Now, find the span of 1 x up to xn in the vector space P, where n is a non-negative integer. So what is the span? So basically, we can write in this form. We can write this one as a linear combination. So to write this, then write this one, then we can write this as solution. The span of 1 x x squared all the way to xn. Xn is basically the same as a naught plus a1x plus an xn, such that a naught, a1 all the way to an are elements of what? Okay, let's look at theorem here, which will not prove it. You can look at it from your textbook here. If V is a vector space and V1 all the way to VP is an element of V, then the span of V1 all the way to VP is a subspace of V. So the span is a small space of V. So you can look at the proof from your book. So basically here you just use the subspace test. I can sketch for you the proof. So sketch of proof. So in this case, you start by the what? The zero vector. So if we let W to be actually the span of V1, and this W is a subspace, so we want to check to, let's say, VP. Now, since 0 vector is equals to 0 V1 plus all the way to 0 VP, then we get 0 as an element of what? An element of W, since it is satisfying. So we still get 0 vector. Almost when you multiply, as that the linear combination. 0 is a linear combination of the 0 vectors there. So it's still in W. So that is the first subspace test. The second one, you can let U and V to be the elements of W, and C and D to be elements of real number. Then find C1, C2, all the way to, let's say, CP, D1, D2, all the way to DP. And these are elements of real number such that U equals to C1 V1 plus CP VP, and V equals to D1 V plus all the way to DP VP. So then U plus V. So this U plus V, you just add this and this, and you will realize that this is in what? This is in W. So therefore, using the subspace test, that means that the span that is a subspace of what? Of. So span is a subspace of. Okay, let's look at a notation here, which we'll be using also. Notation. We define P, and then we put N here to be the polynomial of real coefficients of N degree. So this is basically equals to the span of 1x all the way to xn. And this is a vector space, which is a vector space of all polynomials with real coefficients. So if the polynomial is of degree 3, then we'll get P3. And P3 will be what? 1x up to what? X3. P4 will be 1x up to x6. There's a polynomial of degree 4, degree 3, like that. Okay. Example number 7. And this will be in your third exam. This will be in your third exam. Number 7. Show that W is a subspace of R3. Show that W is a subspace of R3. So I'll give you a question like this. And here you just use the word, the two subspace test. So the major one is actually the zero polynomial. So if it is not satisfying the zero polynomial or zero, and that zero is in the subspace W, then it means that it is not a what? It's not a subspace. So here we want to check whether this is a subspace of R3. R3 are how many entries? 3 entries. So example number 1A, W equals to 3A minus 2B plus C, and then A plus 2C, and then we have B minus C. This is an element of R3, such that A, B, C are elements of real number. So show that this is a subspace of R3. Show that that one is a subspace of R3. Now, if you start by using the subspace test, you put zeros there, A, B, C. It satisfies, right? So that is fine, it satisfies. Now, in this case, if you've seen that it satisfies, then it means that W is equals to what? W is equals to, so we can actually factor out A's, B's, and C's like that. So A, and then for A, we have what? 3, 1, and what? And 0, plus B, we have minus 2, 0, and what? And 1, and then plus C, we have 1, 2, and minus 1. Minus 1, such that what? A, B, and C are elements of what? Real number. And we can write this as, this can be written as span of what? Span of these vectors, which is 3, 1, 0, negative 2, 0, 1, and what's? And 1, 2, and minus 1. So W is a subspace of R3. W is a subspace of R3. Example number 2, just B. W equals to negative A plus 1, 2A plus B, and then B plus 2. And elements of R3 said that A, B, elements of what? real number. Now, if you use the first one as 0, 0, if A is 0, B is 0, then means that we have what? So if we write it like this, then it will be we factor out A, so it will be -1 and all that. B would be like that. Then we have this constant. But if we let some solution. So if we let's say A prime to be equals to minus A plus 1. Okay. If we let that one to be like that. And if we let B prime to be equals to the last one here, B plus 2. Plus 2. We let that. Okay. Now, what is A there? So A will be equals to what? So in this case, okay, so A will be equals to A prime minus A prime plus what? Plus 1, right? And then our B here, our B equals to B prime minus what? Minus 2. So in this case, then W is equals to, okay, so we have this one as A prime, all right, A prime. And then we have our A here is minus A prime plus 1, okay? And then plus B is what? B prime minus 2, B prime minus 2, okay? And then the last one is the B prime, okay? We have like that, say that A prime and B prime are elements of real number. Then, if we solve that, then we have A prime there, and then we have here -2 A prime plus 2 plus B prime minus 2. And then the last one is what? B prime. Such that A prime, B prime are elements of real number. Then, finally, this is what? A prime. The next one is what? Minus 2A prime plus what? B prime. And then the last one is what? B prime. Are you seeing that? Say that A prime and B prime are elements of what? Real number. So if you use the subspace sets there, then it is still what? Satisfying the first. So it is satisfying the first. Now then, this can also be written as you factor out A prime, then it is 1, -2, and what? 0, and then plus B prime 0, 1, and 1 there. Set that A prime and B prime are elements of real number. And this can also be written as the span of -1 of 1, -2 and 0, and what? 0, 1, and 1. This can be written like that. So therefore, W is a subspace of what? Of R3. W is a subspace of R3. So you need to check before you conclude. You need to check if you can let something to be mixed. Will it finally satisfy what you're looking for? So if you are not able to do like this, finally you can just conclude by using the subspace test. Right, and that one is the end of section 4.1. So let's now look at 4.2. Section. Yeah, that 4.1 was very long. Four point two is not so difficult, and it is actually very, very important. Very important. And this 4.2, we look at the null space. So we just check the null space, the column spaces, and linear transformations. So we look at those. So here we will just start from the linear transformation. Linear transformation. So we'll go through the first definition, which we already did previously, but we can still repeat it so that it can stick to your mind very well. If we let V and W, if we have the two subspace, the two vector spaces, be vector spaces. A transformation or a map T from V to W is called a linear transformation or linear mapping from V to W. So basically, it's like just like that. We have the two vector spaces V and W there. So there is that transformation here. That's that transformation. Then if we have these elements U and let's say V to be in V, then when we transform from here to here, then what we get is TU and TV. And this will be in what? That will be in W. So that is the image. So this is the domain, and that will be what? So that is the image over there. So then T of U plus V is basically equals to TU plus T. T of U plus V is basically equals to TV plus. And T of CU is basically the same as C, T of what? For any C elements of real number and UV. And these are in what? Those are in V. So we can combine this and this. So we can combine this one and this one. And this combination will take us to this theorem, which is theorem 1.2, whereby we let V and W be a vector space. A transformation T from V to W is a linear transformation. If and only if T of CU plus dV is the same as CT of U plus DT of for any U and V. These are in V and C and D elements of V. So basically, this is just the same as this, but we have combined with the constant there. So it is the same as it's the same. So you can look at the proof from your textbook. Okay, now let's look at the first example. First example, example number 1. Show that the transformation T from the real or polynomial that to a real number, which is to a vector space, basically to a vector space, defined by T of A naught plus A1 x plus AN minus 1 xn minus 1 plus AN xn equals to A1 all the way to AN minus 1 to AN for A naught A1 AN minus 1 AN element of real number is a linear transformation. So that is a linear transformation. So show that this transformation is actually a vector space. A vector space. And this transformation here, T A naught here is equal to A1. That is equal to A1 times A. So we want to show that that is equals to that. So how can we show this? So we want to prove this in a few minutes. So what we can do is we can let P and Q to be the elements of P, to be Pn, and C and D to be elements of real number. Then P of X is equals to A naught plus A1X plus AN XN. And Q of X equals to B naught plus B1X plus BNXN. Okay, let's do that. Where A naught up to AN are elements of real number, and B naught up to Bn is also an element of real number. Then we know that the transformation, if we multiply Cp plus dq of x, multiply that C, then this is basically the same as Cp of x plus dq of x. It's basically the same as that. Okay. Now we know that P of X is this, Q of X is that, then C A naught plus A1X plus AN XN plus D of B naught plus B1X plus BN XN. Okay. So if we open these brackets here, then this is the same as CA naught plus CA1X plus CANXN plus DB naught plus DB1X plus DBNXN. Then we can collect the like terms here, which is the same as CA naught plus DB naught plus CA1 plus DB1X plus you continue like that until CAN plus DBN XN. Basically, this is XN. So it can be like that. And the transformation now, if we multiply this by a t, then if we put a t here, transformation of CP plus DQ, if we put a transformation there, we transform this, then what we get here is basically C1, which because we are not taking this, so it will basically be C1 A1 plus DB1. If you continue like that until CAN plus DB. And this is basically the same as factoring out C, which is A1, all the way to AN plus D, and then B1 all the way to BN. And this is the same as C T of P plus D T of Q. So that show that this is a linear transformation. So C is a linear transformation from Pn to Rn to Rn. So what are we seeing from here? This T of the whole space here can be written as what? CTP plus what? DTP. So it is basically confirming that that one is a linear transformation. Cool. So we will meet on Tuesday, since you guys said it's holiday on Monday. Then let's meet on. I will post the homework.
The June. Really Juneteenth.
On Sunday.
So we'll
Holidays on Sunday, can't we celebrate it on Sunday?
yeah.
It's not even a holiday.
Well, no one has to work on
I
Sunday, so.
I don't know why I did not know it was an holiday. I could not
Because
be
the
in
holiday's
town.
actually Sunday.
Every Sunday's a holiday.
Right.
Oh, that's fine, though, I'll take another day.
All right, I will check the homework. I'll post the homework.
No, we can't do homework on Thursdays.
No, I will post the homework today,
Okay.
and then you will submit it on. When do you want to
We
submit?
already had enough.
They're not enough. I know there are many.
Mondays was quite a bit.
Since it's
It's pretty easy though.
let it be due on Monday at midnight.
Okay.
And then make sure you send all the homeworks. I'll take time to grade them this weekend.
Okay.
Make sure you complete all the homeworks
Very good.
this weekend. All right.
Good.
See you.
Good weekend.
Mhm.
Very good.